This video is going to cover interpolation and different techniques for interpolation. So I was looking at the Handbook of Mathematical Functions by Abramowitz and Stegun, and early on in the book, there is this section over here that deals with interpolation. Now, just as a quick overview, interpolation is a technique by which you can find a value that's not tabulated on the table. So the sample table is this one right here. The argument is x, and say we have 7.8, 7.9, but we're looking, and 8.0, but we're looking for 7.9527 for the argument x equals to 7.9527. Obviously, we don't have that. We have 7.9 and 8.0, so we're missing that value. So if we want to find the value of the function at 7.9527, we would resort to interpolation. Now, the one standard interpolation technique that we normally see is linear interpolation, and it's covered here. We'll review it. And then the next one is Lagrange's formula. And in this example, they use the 5-point interpolation technique for the Lagrange formula. And it refers us to chapter 25 in this book, which is here. And here we see that it's the 5-point Lagrangian interpolation coefficients. So that a minus 2, a minus 1, a0, a1, and a2 are in the columns. And for a particular value that we're going to find out, the value is going to be called p, that incremental value, we're going to start using these coefficients. So the actual formula for the 5-point Lagrangian interpolation coefficient is here. So we're not going to do that formula. We're just going to read off some values and see if we get the right answer in that example. Now, looking back here, we also see a 4-point Lagrangian interpolation coefficient, and some arguments there for 4-point interpolation coefficients, and even a 3-point. So we'll probably do one of those also to compare, say, the 3-point to the 5-point Lagrangian interpolation, and then compare it also to the linear interpolation to see how close these techniques are to getting to the real answer. So let's get started. Come into the Handbook of Mathematical Functions by Abramowitz and Stegun. And as mentioned before, close to the beginning of this book, we see the section on interpolation. So we see right here our sample table, and the challenge is going to be to find an entry of this function for an argument in between this fellow, 7.9, and this fellow, 8.0. Specifically, the challenge is going to be to find the value of that function for the argument x equals to 7.9527. So 0.527 over what we have here. We have no idea what this function is going to be. So let's go into this now. Now, the one thing to notice is what's contained in this bracket here. That is essentially telling us the error that we're going to have if we interpolate linearly. And it's going to be 3 times 10 to the minus 6. And the number 5 refers to the fact that we'd have to use Lagrange's 5-point system of interpolation to get the full accuracy. Right. So with that, we look into, again, we're trying to find x equals 7.9527, the value for that function. So we go into linear interpolation here. The formula is this one. Okay, what have we got here? Well, p is the 0.527. You can derive it with this, but it's essentially the little delta over 7.9 that we're interested in. F0 is the value at 7.9, and F1 is the next value of our function at 8.0. So now following this equation right here, we plug and chug. We see here 1 minus p, which is 1 minus 0.527, times the first value, F0, which is this one, and plus p, which is 0.527, times the value of the function at 8.0 here. So after we multiply and add, we end up with this value. Now, remember, it is known that there's possible error of 3 times 10 to the minus 6. So because of this thing in the brackets here. So we essentially chop off the last 4 entries here of this answer. And we're left with 0.89773. Great. before we move on to the spreadsheet where we're going to show this in summary, we look at Lagrange's formula. Now, Lagrange's formula can be used for 5-point interpolation or 4-point interpolation or even 3-point interpolation. Either way, the formula pretty much is f, the value that we're looking for, is these coefficients, the a sub n's, times the f sub n's, the values of the function at a particular place. So in this case, for the 5-point interpolation, is a sub minus 2 times f sub minus 2 plus a sub minus 1 times f sub minus 1, and so on, all the way up to a sub 2 times f sub 2. Right. So we have to know the values of the f's. Like before, the values of the f's are the values of the function here. So we'd have to get 5 of these entries around the value that we're interested in. And the values of the a's, the book here tells us we need to go to chapter 25 to find the values for 0.52 and so on. So if we turn over here to archive, so as not to bring in a copy of the book, we see in page 903, we start seeing 4-point Lagrangian interpolation coefficients. And here's the 5-point Lagrangian interpolation coefficient. Specifically, that's it for 0.52. So if you think about it, we're going to be looking at these values right here. And also, because it's between 0.52 and 0.53, remember, we're looking at 0.527, it's going to be in between those two. So essentially, let's highlight these and these. Now, the tricky part about this approach is that we have to do a lot of manual entries. Specifically, we have 10 entries to put in, and we will. But just FYI, when I was doing it, I made a typo on at least 2 figures. So this can be a source of error. If we go back a page on the Handbook of Mathematical Functions, chapter 25, we see the 4-point Lagrangian, and then over here we even have the 3-point Lagrangian interpolation coefficients. Again, going back to our formula, these are the coefficients times the value of our function, and so on. So, okay, with that, let's go into this. This is a summary of the different formats that will allow us to interpolate. The first one is the linear interpolation. If you remember, over here, it was this fellow right here. So I've just noted it here. 1 minus p, and then these are the values of f at 7.9 and f at 8.0. Multiply these together and get that. Multiply these together and get that. Add these two together and get that. And again, if we add these two together, we get the 4403 at the end, which they warned us in the book, in the Abramowitz and Stegun, that we don't have that information beyond 3 times 10 to the minus 6. So we chopped off the last digits. So, okay, easy enough. That's our first approximation. That's normally what we would use. And for many applications, that may be enough. But in some applications, it's necessary to get more precision. Where, if you're looking at frequencies, for example, you're looking at megahertz or gigahertz, you might actually care to see, 9 significant digits or something like that. If you're looking at orbital mechanics problems, you can definitely be looking at very precise requirements there. Right, so without going too much into the motivation of this, see here we have the 3-point Lagrange interpolation, and we find these values for p equals to 0.52. So if we go back here to the archive.org information, we see for 0.52 we have these values right here. See if I can highlight them. Yeah, it's going to be a bit difficult. But you see 0.52 is 0.12480, and that's it right there. The next one is going to be for A0. 0.52 is going to be right here, 72960. That's that one. And lastly, we have this one over here, 39520 for 0.52. So that's where that comes in. The values of the functions are, as we saw before, 737, 4302, 7113. So that's where that comes from. Multiply this times this like before, you get this, this times this times this. You add them together and you get that number. So we do the same thing for P03. Sorry, P equals to 0.53. So we go back here, we just type in these numbers. The negative 12455 is here and so on. So you get these two numbers here. Now, once you have these two numbers, this is where it gets a little bit interesting. For even though we're doing 3-point Lagrange interpolation, we have to interpolate linearly between these two. So this is what this step right here is all about. So we're going ahead and saying 1 minus P being 0.7. Now, because we've got it up to 0.52, we need to do the interpolation to 0.007. So 1 minus P, and this is P, 0.7. The value here of this, the value here of this gives us this. So that's our final answer for 3-point Lagrange interpolation. Similarly, we're going to do the 4-point Lagrange, and we get this number. And finally, we do the complicated one, the 5-point Lagrange interpolation, which the book told us will give us the most precise answer here. So again, we read this value here and this value here, and we get those coefficients, 2339, 583, etc. And then so on. The other ones, 4.52. And here we see the values for 0.53 starting at a sub minus 2 of 2334, 37838, 2334, 37838. Right, so here is these values, If we do that, well, there we go. So again, we multiply these a sub minus 2 times f sub minus 2, a sub minus 1 times f sub minus 1, a sub 0 times f sub 0, a sub 1 times f sub 1, a sub 2 times f sub 2. Add them all together and get that number for 0.53. Similarly for 0.52, linear interpolation step just like before for the 3-point Lagrange interpolation to get that number. So that's as accurate as we can get right there. This one right here is not going to be as accurate, but you start seeing that 4-point interpolation almost gives us the right answer, down to the last digit, really. And notice over here that we could argue about this 3 right here, which in the book is doing the interpolation here. It gives us a 2. So what gives? Well, if you look at it, and if we select the ribbon and we can do the resolution of this, we notice that we have one extra step here. So if we do this, there it is. There's the 2. So we're just rounding up right here. But so there's nothing really, strange about that. This is the value, this is the answer that we get for 5-point Lagrange interpolation, for 4 and for 3. So you start thinking that for 3, we start losing the values here at this point. So definitely better to do the 5-point Lagrange interpolation. And this is how we do it. This is how we get to the answer. Let's remove the ribbon so you can see all of the work that we've done. And again, this is just a way to actually get from the Handbook of Mathematical Functions the Lagrange formula for interpolation for 5 points and how to get our answer. Again, the resolution is quite high here. And in some cases, when we're dealing with very specific precision problems, that might be required, which is why we're doing this really fancy interpolation. In many cases, this will be enough. The linear interpolation might do just fine. But there is this other system of interpolating that is worth looking into. All right, so 5-point Lagrange interpolation. Hopefully you found it interesting and useful.